mean, think about it. It's an element of total extremes. It's the building block of the softest pencil lead and the hardest diamond. We are talking, of course, about carbon. Yeah, I know. It sounds like the setup to a really weird joke, right? But it's a totally serious scientific question. So what is the connection between a glittering diamond, the gasoline in your car, and, well, you? The answer is a single, pretty humble element, carbon. And that's what we're diving into today. Now, you'd think something this important would be, well, everywhere, right? But here's where things get interesting. This is the first big twist. In the entire Earth's crust, carbon only makes up a teeny tiny 0.02%. It's mostly just locked away in stuff like coal and petroleum. That's surprisingly small. And it's pretty much the same story if you look up into the atmosphere. The carbon dioxide in the air, that's just 0.03%. So when you put it all together, this scarcity, both in the ground and in the air, it leads us to a really fascinating puzzle. And here it is, the carbon paradox. How can an element that's actually pretty rare on our planet be the absolute foundation for, well, everything we rely on? Our food, our clothes, our medicine, us. Every single living thing is built on a carbon framework. I mean, the scale of carbon's influence is just mind-blowing. Chemists have found millions of different carbon compounds. That's more than all the compounds from all the other elements combined. So how in the world does it do it? What is its secret? Well, the answer is all about how it makes friends, how it connects with other atoms. So to really get a handle on carbon's power, we need to look at how atoms form these relationships. It really all boils down to a simple choice. Do you give, do you take, or do you share? Okay, so there are basically two main ways atoms can bond. First up, you've got ionic bonds. Think of table salt. One atom literally gives an electron away, and another one takes it. Bam, you've got this super strong attraction. But carbon plays a totally different game. It doesn't give or take, it shares. And this sharing creates something called a covalent bond. And this whole pact of sharing idea, it's the key to everything. When atoms share electrons, they can link up and form really stable molecules. It's kind of like a business partnership, you know? Both sides put in some capital, and together they create something new and strong. This covalent bond, this is the first big piece of the puzzle. And this sharing isn't a one-size-fits-all deal. It happens at different levels. Atoms can share one pair of electrons, that's a single bond. Or they can share two pairs, making a double bond. That's what holds the oxygen we breathe together. They can even share three pairs, creating this incredibly strong triple bond, like you see in nitrogen gas. And the cool part? Carbon can do all of these. But just sharing electrons, that's not the whole story. Not even close. Carbon has two very special properties. Two, well, let's call them superpowers, that make it the master architect of the molecular world. So let's break them down. Okay, superpower number one, tetravalency. Tetra just means four. A carbon atom has 4 electrons in its outer shell that are just itching to be shared. That means it can form 4 strong covalent bonds all at the same time. Think of it like the ultimate Lego brick, the one with connection points on all 4 sides. It can build up, down, left, and right, creating these amazing, complex 3D structures. That right there is carbon. And then there's superpower number 2, which is even more special. It's called catenation. This is the really unique bit. It's carbon's ability to form strong, stable bonds with other carbon atoms. It can link to itself over and over again, creating these long chains and complex rings. Now, some other elements can do this a little bit, but nobody, and I mean nobody, does it like carbon. The bond between 2 carbon atoms is just incredibly stable. And here's a perfect example of this catenation in action. You start with methane, that's 1 carbon atom. Then you link another carbon to it, and boom, you've got ethane. Add 1 more, you get propane. Another, you get butane. You see the pattern? These chains can just keep going, building this huge variety of molecules from the exact same simple pieces. So you take those 2 superpowers, the ability to form 4 bonds and the ability to link to itself, and suddenly carbon has this toolkit to create an almost infinite number of molecular blueprints. Let's take a look at how this gets even more complex. Okay, and this is where it gets really, really cool. You can have 2 molecules with the exact same parts list, the same number of atoms, the same formula, but they're just arranged differently. Our source material calls these structural isomers. It's exactly like having the same pile of Legos, but you build two totally different things. Same parts, different final product. So you see, carbon isn't just stuck making simple straight lines. No way. It can form branch chains that spread out in all directions. It can even loop back on itself to create these super stable rings. And these structures can be built with just single bonds, we call that saturated, or they can have double or even triple bonds thrown in, which we call unsaturated. The architectural possibilities are just endless. Okay, so let's bring all this theory back down to Earth. How do these simple rules, how carbon bonds and build structures, result in the incredible variety of stuff we see all around us? I mean, from a simple pencil to, well, to life itself. This might be the ultimate example of just how versatile carbon is. Think about it. On one hand, you have diamond, the hardest natural substance known to man. And on the other, you have graphite, the stuff in your pencil that's so soft it just rubs right off onto the paper. And here's the kicker. They are both 100% pure carbon. So what's the deal? The answer is all about the arrangement. It's just geometry. In a diamond, every single carbon atom is locked into this super rigid 3D grid bonded to 4 other atoms. It's like an unbreakable fortress. But in graphite, the carbon atoms arrange themselves into flat hexagonal sheets, kind of like layers of chicken wire. Each atom is only bonded to 3 others in its sheet. The sheets themselves are strong, but they can just slide past each other really easily. And that one difference in structure, it leads to completely different properties. Diamond's rigid fortress makes it insanely hard, and it won't conduct electricity at all. But graphite's slippery layers make it soft, and because it has some electrons that can move around between those layers, it's actually a pretty good conductor of electricity. Same element, 2 totally different worlds. It's all just geometry. And finally, let's remember, carbon doesn't just bond with itself. It's a really friendly element. It loves to form strong bonds with other elements, especially hydrogen, oxygen, and nitrogen. And by attaching these different atoms to its chains and rings, carbon creates this infinite library of molecules. We're talking everything from simple sugars all the way up to complex DNA. These are the literal building blocks of all life as we know it. And really, that's the ultimate takeaway here. From just a couple of simple rules, sharing 4 electrons and linking together, carbon has managed to create the entire breathtaking complexity of biology. It solves its own paradox, right? It takes this relative scarcity and turns it into the foundation for an endless variety of forms. It really makes you wonder, doesn't it? What else is possible? What other wonders, new materials, new medicines, new technologies are just sitting there, waiting for us to build them from carbon's simple yet powerful